Okay, so at the end of last class, the, what we had started to do was we had started to do basically retrosynthesis, and this is basically working backwards. And typically what you would, one of the rules that we had when we were working backwards was that you want to install reactive functional groups last. And by doing so, you basically avoid side reactions throughout the synthesis. Because if you've got a functional, if you install a functional, like sorry, a reactive functional group at the start, then every reaction after that, you always have to worry about it reacting versus what you want to have reacting. So I think at the end of, and so one of the things that we did at the end of last class was how to make carbon nitrogen bonds. In organic 1 and 2, one of the things that we did was basically SN2 reactions. And so you would have some amine and you would react it with some alkyl halide of some type, and hopefully you would make your, say, a secondary amine. Now, the trouble with this is that there are potential side reactions with this, one of them being over-alkylation. So secondary amines sometimes are more reactive than primary amines. So this reaction isn't always reliable, I guess is the word I want to say about. So then there was a couple of other ways that we came up with making amines. Does anyone remember what they were?
Using cyanide ions.
Right, so this would be an SN2 type of thing, but the difference being if you had, say, using a nitrile or a cyanide and doing an SN2 on a RX, so you would make and you would need to basically reduce this reduction. Doing this, you insert, there's actually, you've got a CH2, which is added as well. So there's an extra carbon. That's one of the things you need to keep in mind. So that was one way. And so this way is still relying, it still has the, if it's an SN2 reaction, it's got the limitations associated with an SN2 reaction. So it's got a limited number of, it's the alkyl halides that you have to be concerned about. Only certain ones will work well. What was another way of doing, making amides? I mean, amines.
Can you make like an imine and then reduce that?
Right. So reductive, right, reductive amination. So here you'd start with, say, a ketone plus your amine. Do a primary one for this example. This loses water during the course of the reaction. You make your technically the reactive species in this reaction is this guy, the imine, and it is reduced with sodium borohydride, cyanoborohydride to your, say, secondary amine. So that was, so in this case, you'd use a carbonyl compound plus your amine. So, right, so carbonyls, so the main ones would be ketones or aldehydes. And so these are different than, say, the alkyl halides that would be used for the other routes. And for your amine, technically your amine could be primary or even secondary. So that's good. There was one other way, and I'll write it. Where will I write it? Oh, the cyanide items is right there. The other way is, so the oximes, this is very similar to the imine and the oxime. The fourth way is what we did here, which is the reduction of a amide. So you make your amide, which is not a reactive, particularly reactive functional group, and then you can reduce it with lithium aluminum hydride or borane to make your amine. So, and the neat thing about that is that, again, you still be using a primary amine, but now you're using an acid chloride. So, and you can even make amides actually from esters too, but these are the easiest ones to work with. So those were some neat ways of making amines. And I think the last thing I said we could do was this compound here. To make this, there's a couple of ways you could do it, depending upon how you, where you broke the bonds. Probably the most interesting bond to break, you'd probably break this one. And the starting material here, if I was to do this, I would probably use a ketone plus an amine, primary amine. Do a reductive amination there. Then we'd have to figure out a way to make this, which we will get to a little bit later on. Okay, but I think the thing we were going to do next was, if you ever need to use H2N minus. So this is the sodium version of this. We would have used this in organic too relatively frequently, and it's commercially available. You can buy it probably in a bottle of THF. But the thing is, it's extremely basic. So because it's so basic, it isn't particularly useful for, like, if you wanted to do it, let's say you had this and you wanted to make this using NaNH2. The main, so this would be an SN2 reaction. The main problem here would be that you would get an awful lot of E2 elimination, and so it won't be particularly useful. So chemists have developed other ways of using this that aren't as basic. One is sodium azide, and azide can be reduced using H2 or sodium or lithium aluminum hydride, and then there'd be an acidic workup with this, and that will generate a primary amine. The limitation here is that this is an SN2 reaction, so it's limited in that sense. Azide, remember, is this. So negative plus negative. It's a really good nucleophile. Linear. It's actually got 2 nucleophilic ends to it, so it's a nice little reagent to use. The other way, the classical version, is using this ion here. This I don't even know how to pronounce it properly, so I'm not going to. And this is a it's just what I would call it's a pretty soft nucleophile. You've got nitrogen with a minus, but this is it's resonance stabilized, and this is actually an SN2 type reaction as well. So same sort of limitation. And you make a nitrogen carbon bond, and then you release the rest of this molecule using hydrazine. So you're breaking both of these bonds, because hydrazine, this is a relatively good nucleophile as well. It's basically going to attack electrons move up, electrons move down, transfer a proton, and this is going to happen twice because each one of these can attack each carbonyl, and that would release your amine. Yeah, that's a pretty historical version of it. So we'll see this in some of our older syntheses. Okay, now it's funny, some of the simpler reagents that we would want to use have got some challenges with them. So another one is H2S. And so you take, well, this is toxic, so you don't particularly want to use that. It's also a gas, so that makes working with it problematic. But this acid-base reaction would work great. HS minus, this is a super nucleophile. So substitution reaction would work really well. You've made your thiol. Now the only problem is that if you still have some of your base in the reaction, it's going to quickly deprotonate the other side, and then this is a really good nucleophile. You have an alkyl group sort of pushing electron density, which would make it even more nucleophilic than this, and you bingo bango, you've got overalkylation. So it becomes a problem. So there's lots of issues with this. You're working with a toxic substance which will kill you really quickly. It's a gas, and it results in overalkylation. So the thiourea is basically how we overcome this. So thiourea is this structure here, and it has the benefit, if you think of like resonance structures and this type of thing, that there is a lot of electron density associated with the sulfur, because both nitrogen atoms can donate electron density, and so resonance, there's tons of electron density on the sulfur. The sulfur is we call it polarizable molecules, which makes it a really good nucleophile. So when this sulfur attacks, let me draw it like this. So this is SN2. You generate a intermediate which now has a positive charge. And this positive charge, let's draw it like this. Call that R. And we can draw so the reason why I've drawn all these little dashed lines like that is that you can draw resonance structures that would stabilize this positive charge. So it's spread over a number of different molecules. So that's why it's drawn like this. Then this is a hydrolysis reaction. So it's just taking water and like hydroxide, and that releases your thiol, and it generates urea. And so in that sense, if you're interested in that, just think of water attacking here, these electrons moving up to have a carbon which is bonded to this would be hydroxide actually. So you'd have this. Oops, get rid of those. And then it's basically, you could do this two ways, I guess, since it's under basic conditions. We would want to deprotonate our most acidic proton, which would be this one. And then the negative charge would push out, you'd have as a leaving group. And that would subsequently get protonated if you did an acidic workup. So yeah, so thiourea is a way of making to install as an equivalent to HS minus thiourea. Okay, so what were the 3 guidelines from last class?
Break near a heteroatom, like connecting a heteroatom.
Right, so break beside a heteroatom. So that's why we were looking at like the nitrogens and the sulfurs. You want to use known reliable reactions. That was another one. And then the third one was if you want to install the most reactive sort of group last, so you don't have these side reactions or chemoselectivity issues. The fourth guideline is what historically people would call 2 group disconnections are better than 1. So, oops, what am I doing here? So if you're basically synthesizing a thiol ether here, we would say that this is the better disconnection because you would use, because phenyl, remember phenyl is an aromatic ring. So S minus plus the positive charge here. So you would have SH and then the bromine, and this would be a SN2 reaction. The issue you would, that would be the way of doing this. You hope you don't over-alkylate it, but that would be, so if sulfide A, I guess I should point out, where's sulfide A? Sulfide A is this guy here. Not helpful here. So if this is your target molecule, it's basically an extension of this same reaction. All we've done is we've added a carbonyl here. So if we were to use the same methodology, break this and have negative and plus, this would seem like, oh, we could just do an SN2 reaction on this molecule here. And what a two-group disconnection is basically saying is that if we're doing this, we're actually ignoring this carbonyl, which could play an important role in the reaction. Particularly, it's going to reduce the number of potential side reactions. So a two-group disconnection in this case would be to use this ketone in this reaction so that it helps out with regard to side reactions and that sort of stuff. So if you want to use this as your reagent, rather than putting a bromine on that, which would be kind of hard to make or more of a challenge to make, you could use an enone. If we think of resonance structures of enones, we've got this is one resonance structure. And we could do another resonance structure, which involves oops, wrong. Negative plus. And so the positive charge here is right on the carbon, which we were for our idealized reagent. And so this reaction is what we would call a 1,4 addition. So basically 1, 2, 3, 4. So we're attacking this position 4, and so 1,4 addition. The other name for 1,4 addition is sometimes called Michael addition. Right, so the selenide comes here, those electrons move up, you've got this, and then this structure here, if we're looking at this little bit here, this is what we call an enolate, and this will quickly be protonated by any acidic protons that happen to be in the reaction. And you've got this is your product, and now you've got more of this, which can go on and attack another starting material. So you only, in this reaction, you'd only need a catalytic amount of base to actually get the reaction going. So the advantages of this are basically you don't waste a bromine atom, so you don't need a leaving group. This basically, this enone is, the enone itself is electrophilic enough. So there's a big delta plus here, there's a delta plus here. And then basically both of these, the two functional groups cooperate in making this carbon silicon bond. And then the final bit is that just a catalytic amount of weak base is required. So we'll talk about the side reaction in a second, but if we're thinking about this reaction in the sense of, okay, you've got your enone, you've got your thiol, and you've got a small amount of base. Versus if you've got your bromide, you've got your thiol, and then you've got your base. We just did that little exercise with regard to lab yield, right? Lab. And we talked about things like atom economy. That was one of the sort of metrics for like a high yielding reaction and that sort of stuff. So if this is reagent A and this is reagent B and our final product is down over here, star, we are basically losing a large atom, bromine, good leaving group, useful, but from an atom economy standpoint, this reaction is going to be quite low. It's not going to be very good. Whereas if you've got these reagents here, like an enone plus this thiol, now the atom economy of this reaction is going to be much higher. So it's lots of favorable things with regard to that. When we're talking about some of the other processes, like do you need a catalytic amount of a base or a stoichiometric amount of base, all of those other metrics, if you've just got a smaller amount of this base to run the reaction, all of those other metrics, the yield is going to be higher in this, using this two-group disconnection, while using the chemistry of the enone to help make this bond. All of those other metrics are going to be better. So this is why when the general sort of rule of two-group disconnections is better, there's usually a host of reasons which make this the case. And there is a possible side reaction here. If you tried to make this bromine and you didn't deprotonate your thiol first, and you just had, like, say, hydroxide, there is a real possible side reaction of you eliminate this, and then you end up making this thing anyway, which is a better reagent in itself. So now the problem is, what is a two-group disconnection, and being able to visualize these. So the next part of this is just trying to figure out where these exist, because they aren't quite evident just looking at things. So one of the rules is that on a carbonyl, this carbon's called the alpha carbon, the one right next door to it, and this one's the beta carbon. If you've got a nucleophile on the beta carbon, then Michael addition is Michael, or 1,4 addition is totally warranted. And so these would be things which have like oxygen, nitrogen, sulfur, and so heteroatoms, plus actually even carbon atoms. So, because you can use organocuprates, they are, they selectively do 1,4 addition. So an organocuprate, if you don't remember, looks something like this. So you'd be transferring one of these R groups, and it's basically a copper lithium sort of species. We'll see some of these in the future. But so if you've got a nucleophile on the beta carbon to this could be a ketone, this could be an ester, even an amide, 1,4 addition is possible. Aldehydes, not necessarily as useful, because aldehydes are quite a reactive functional group. So let's keep that in mind. So recognizing two-group disconnections. Great. So this nomenclature here, so you got a heteroatom on 3 carbons away. So this would be the alpha carbon, this would be the beta carbon. This would be an appropriate relationship to work. So 1,3 di-X relationships are for Michael addition. So if this is our example, so we got a pyrrolidine ring plus an ester. So if we draw this out, so it's so here's our ester, alpha carbon, beta carbon. So if this is the bond we're breaking, basically 1, 2, 3. It's 3 bonds away from the actual carbonyl itself. I kind of don't like the way that this is, but if you, it's good for numbering stuff, so I shouldn't really complain. So, so that is one. Now, next question. What if there's no carbonyl adjacent to the thing? So if you've got a molecule like this, so you got 2 heteroatoms and they are 1, 2, 3 carbons apart. All this can be is basically you're just a functional group manipulation away from this. So this alcohol, remember, can be oxidized to a carbonyl. And specifically, this would be ester. Remember, primary, like if you got an ester, reduce it, you get primary alcohols. So then this structure is far easier to see that 2-group disconnection. So functional group interconversion, which is a reduction. You've got your ester on the alpha, beta carbon, break this bond, and you've got your enone in a primary alcohol. So if this was our synthesis, Michael addition 1,4, lithium aluminum hydride, and you've got your alcohol here. All right, let's look at this one. Primary amine, and let's actually hide this for a second. So on this molecule here, which we will highlight in green, we've got 2 functional groups that are important. One is the ether. The second is the amine. So if we think back to our guidelines with regard to chemoselectivity, the amine is the thing we want to install last, because this is the reactive. This is the reactive functional group. The ethers are solvent, so we hardly ever use those as, like, it's not really a, it's just a structural feature of a molecule as opposed to a reactive functional group. So, and there's a couple, this is just one of the ways that this could be done. There's another possible way, which we'll get to in a little while. But if we think back to when we were making our primary amines, our good old friend, the cyanide, and the other nice thing here is that, let's erase this for a second. So if we convert carbon 3 to a cyanide, then you've got carbons 1 and 2, and they can have the double bond. So a cyanide, a conjugated nitrile, let's draw some resonance structures of this. So light blue. we've got a pi bond between carbons of different electronegativity. Let's draw this first one. Then the second resonance structure here, we have got a positive charge beside on the allylic carbon to a pi bond. Let's move that over. And then this gives us positive charge. So this is exactly analogous to a enone. So 1,4 additions can take place with like nitriles, conjugated esters, so as long as it's got this similar sort of motif as the carbonyl, where you got an electronegative atom where the electrons can be pulled towards, same sort of thing can work. So in this synthesis, you need a bit more, the alcohol, this proton's a bit more acidic, so sodium hydride, that's going to specifically remove that. Then you can do the 1,4 addition, and then you need to hydrogenate this, and we're using a catalyst that's a bit more, it's got a bit more reducing potential than just say a simple hydrogen and palladium on carbon. That's not quite strong enough. You could also use, in this case, lithium aluminum hydride. And then the second step would be an acidic workup, H3O plus, so 1, 2. So two group disconnections are better than none. Now, one of the most common ones is the 1,2. So when you've got heteroatoms, 1, 2, 1, 2, 1, 2, that are, so there's 2 carbons in between them. And this would be it. There is 2 reagents that are particularly useful in this case. And you could conceivably use something like that, actually not with this one, but for this, no, I'm thinking something different. So the one thing which is common in all of these is that we've got, on carbon 1, we've got an alcohol here. And so if we break this bond here, 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 or here, we would have whatever our heteroatom is, X and this. And we may say to ourselves, well, this is a perfect sort of reagent right here. Now, the trouble is with this, of course, we go back to the whole atom economy thing. But there's no reason why this oxygen itself can't be attached to that positive charge. So the great reagent for this sort of is an epoxide. And there's, so when we talked about rings, let's go back to rings here for a second. Cyclobutanes, cyclopropanes, cyclopentanes, cyclohexanes. All of these rings aren't created equal in the sense of stability. Certain rings had something that was destabilizing toward them. It's got a certain type, it's got a name for it. We remember what that name is? And it starts with the word ring. Blank. And these guys have it. And
Is it strain?
Ring strain, right. So when you've got a 4-membered ring or a 3-membered ring, there's a strain basically built into the molecule, because this is basically an equilateral triangle here. So the bond angles are all wrong for a for an sp3 hybridized system. So, because that would normally be like 109 degrees, and these things are essentially at 60 degrees. So there's a strain built into this molecule here. And so if you've got some nucleophile like this nitrogen attacking it, one of the things which you're going to be releasing all of that ring strain, and that's going to be a energetically favorable reaction. So epoxides are often used as a two-group disconnection here. So carbon 1, carbon 2, and you can open this up and generate the product that you are interested in. Now, the next thing I've got is basically a cautionary tale here. So if you've got an epoxide, with this one, doesn't matter because each carbon A and carbon B are exactly the same. But if you want your nucleophile to attack, so we've got two regioisomers here, and here, you've got to set up your reaction in a fashion that will open up, that the nucleophile will attack the appropriate carbon if it's unsymmetrical to give you the product that you want. So this is one of the cautionary tales that takes place. So essentially epoxides, they will, if it's under basic conditions, they will open at the least hindered carbon. So if you wanted to make compound on the right, this is fine because your nucleophile, I guess I shouldn't have called it X. Your nucleophile is attacking the least hindered carbon, number 2. But if you wanted to make the compound on the left, then we would have to make sure that we used different reaction conditions to make this work. So that's just one of the things to keep in mind there. So here is, yeah, this is like actually a good place to stop because we're just about out of time. So I promise next class we'll do a bunch of top hat questions, but these are two really interesting molecules. Propropanol, gosh, I can't pronounce that properly. This one and this guy. We actually tried to make these in the lab like many years ago, and both of these are going to have two-group disconnections associated with them. So think about those a little bit. So what's interesting here is we're going to name it 1, 2, 3, 1, 2, 3. So you've got heteroatoms on each of those carbons there. Yeah. Actually, there's a yeah. So think about, so you actually have heteroatoms on each carbon, and so one of these two-group disconnections is actually going to be quite useful to make this work, and we'll discuss that a bit at the start of next class, unless there's a question immediately.
I have a question about the dry lab.
Okay.
I'm calculating the PMIs and they're really, really high. Like, they don't make sense. I don't know if that's...
Yes, that's typically, you want, I think industrially, what they want the PMIs to, there's a certain range they want them to fall in between. I think it's between, like the lowest you can go is best, but I think like the maximum they want is around 120 or something like this. So if you have something which is 200 or above, that's normal, I would say. Because we're not, because when it comes to us working in a lab doing a reaction on a small scale, we're not paying any attention to this at all. So But when it comes to process chemistry and like say at a pharmaceutical company, then they would be really, really, really interested in getting that number as low as possible. So if you do get a really big number, that's not
Like
that's
it
not
doesn't necessarily mean I'm doing it wrong.
that's right.
Okay, and also just, do we want to include every single thing that's in the workup and the reaction for that? Like for experiment 2, it says it was filtered through a pad of cellite, which is 10 grams. Like, would I include that?
Yes. For the PMI one, yes.
Yeah. Okay.
I had a question about actually the labs, because some of the, like, I'm coming in next Tuesday, but I'm not till 3:40. Are the doors to the Brody building going to be open to get in?
Yeah. So do you have a student card?
Yes.
Okay. I think that so the way that they're doing it is that those doors open up 20 minutes before and 20 minutes after a lab is started, and most of them start at 1:40. So I'm gonna have to go downstairs. Just let me know what time you're gonna show up at. Like if you're showing up at like 10 minutes before the lab starts, I'll have to go down there and let you in, I think.
I was also going to ask this because I don't have a student card because I haven't been to this school at all. So
And when are you scheduled? You're not until
I
the
know it's not today. I think it's like the last rotation of
I
the
think
lab too.
right. You might want to look into getting a student card at some stage.
Yeah. I'll maybe take a look at that. But I have a lab on Wednesdays with Chen, and I haven't had a problem getting in so far. So
Right. Okay. So yeah, you guys will be starting at 1:30.
the big thing is you're not allowed to like only one person in the elevator at a time.
Right.
That's the only really big rule I noticed, and you have to wear a mask the whole time in the building.
Right.
So like 3-hour lab, 3-hour mask, good times.
Well, the lab won't take that long.
Okay.
Yeah.
Oh, what is it just in the regular organic chem lab?
No, it's in 419, which is right across from my office.
Is that that's your research lab?
Yeah.
Okay, yeah.
Was there anything else? So I think
Oh, sorry, I was gonna ask, that dry lab, is that due when we go in for our lab, or is that due like today? I can't remember.
it was supposed to be due today. So
Okay.
if you can do it today, that would be super.
Yeah, no, I just didn't know when you wanted to hand us in. Like, did you want it handed in like before we came in for our first lab, or?
I hope to be able to get them marked and handed back relatively soon.
Okay.
Yeah.
Dr. Hill, do we need to show calculations for calculating like moles and stuff? Like the millimoles stuff?
No, I don't think so. As long as, I mean, yeah, no.
Okay.
Because I assume everyone does that anyway, right? So no, I think that's just going to take up space. But if you did that, that's fine. Okay, so I'll see a few of you in about an hour and 10 minutes or so, and then I'll go downstairs at around 3:30 or just slightly before that to get the doors open for the second group today.
Goodbye, Dr. Hill.
All right, have a good afternoon.
All right.